Let's look at the next topic, which is linear independence. Before we start discussing linear independence, let's look at what are linear combinations of vectors. So let's say we have vectors v1, v2, etc., vn, where each vi belongs to space Rm, like it's an m-dimensional vector. And I varies from 1 to 2, etc. n. So there are n vectors, and each vector is an m-dimensional vector. Let's say we have scalars pi belonging to R. I is equal to 1, 2, etc. n. Then y such that sigma I is equal to 1 to n ci vi is a linear combination. Okay, so we can form a vector y by using the linear combination by scaling each vector by scalar ci and adding them all together. So it's the linear combination of these vectors which will give us another vector. So this is known as a linear combination of vectors. So another way of representing this linear combination of vectors is we have a vector y, and we can stack these vectors along the rows, sorry, the columns of a matrix like v1, v2, etc., vn, and we multiply it with values c1, c2, etc., cn. So basically what this does, so we have an m cross n matrix, not these dimensions. We have n vectors. So the columns of the vector, number of columns of the vector will be n, and each vector is m dimensional. So it's the m rows and n columns, and what this dimension of this matrix. Let's call this matrix as A, and let's call this matrix as, let's say, C. Okay, so the dimension of this matrix is eventually C will become like a vector. This will be an n cross 1 matrix. So what will be the resultant? Resultant will be an m cross 1 matrix. M cross 1 matrix. So the resultant y is an m cross 1 matrix. So all these vectors are actually m cross 1 vectors stacked along the columns of a matrix. So what we have to note here is the vi which we had was in Rm. So y will also be a vector in Rm. This is also an important thing to note. Okay, this is one way of doing it. So why this is the same as linear combination? Because this is how we can view matrix multiplication. So one way of viewing matrix multiplication with a vector is to stack. If you consider each column of a matrix as a vector, then the multiplication can be viewed as scaling of each vector. This is C1 into V1, the vector, plus C2 into V2 is etc. plus Cn into Vn. Is the final result y, which indeed is an m cross 1 matrix. All these are m cross 1 matrices. Okay, this is one way of looking at it. Okay, fine. So we've seen what linear combinations are. Let me put it a bit more accurately. This is linear combination of vectors. Okay. If you know linear combination of vectors, then you can actually define linear independence. Okay, let's do the linear independence of vectors. So how can we define linear independence? Let's say the n vectors which we had as earlier, that v1, v2, etc. v1, vn are vectors which belongs to Rm. Similar setting which we have as earlier. We're taking a similar linear combination of vectors. So let's write it more systematically. C1, C2, etc. Cn belong to R. Could be any field. Need not be always R. Unless I'm specific about it being a complex or real number. Could be any field. Interesting question. We'll see, suppose it's a complex number. How do you take the linear combinations? Simply, I think you can distribute it over the real and uh, complex axis of the complex number. So I think it's fine. You can do it, doable. Okay, let's say these are the coefficients, so the scalars. Then similarly, we take this linear combination, sigma, ci, vi. It's a linear combination, okay? Then if you take linear combination, if it is 0, okay, we took the linear combination, like what we had in y. Okay, let's use the same setting. Let's say y is the linear combination of these vectors. I is equal to 1 to n ci vi. The linear combination, this is one linear combination vector, and it appears that y is equal to 0 when only if c1 equal to c2, etc. is equal to cn equal to 0. Then v1, v2, etc. vn are linearly independent. So what does this mean? We have multiple vectors in space. Okay. So whenever we're scaling it, it gets scaled with some value. Like this is v1, this is c1, v1. Let's say this is c2, v2, v2. So whenever we are scaling, we're adding these vectors together, we have to use parallel of vector addition. Doable. Okay. Finally, the resultant vector turns out to be this. So what does linear independence mean? If only the combination, if this resultant has to go to origin or 0, let's say the 0 vector, the only way we can scale this is C1 has to be 0, C2 has to be 0. But is there another way we can scale this up? For example, these two vectors which lie on the same line, or not necessarily this, when these two vectors which lie on the same line. So you scale it by, let's say, v1 and v2. And v1 is equal to 2v2. I think it's the other way around. v2 is equal to 2v1. How can you make the linear combination equal to 0? Then let's say take v1, 2v1 minus v2, 0. So what are the coefficients here? 2 and minus 1. So with these with this scalars, 2 and minus 1, we could reach the 0 vector. Are these vectors linearly independent? No. v2 and v1 are actually, they are linearly. So how do you coin that term? if this condition is not satisfied, then you call this as linearly then in this case it is linearly dependent. This is linearly independent. Okay, so how is linear dependence defined here? It follows from the definition of linear independence. So if V1, V2, etc., Vn are not linearly independent, then they are linearly dependent. This is how linear dependence is defined. Hope this is clear. You can even extend it to other dimensional vectors. This is less. I've taken a two-dimensional vector, you can extend to three-dimensional vectors as well. So this is the idea of linear combinations, linear dependence. I think we can wrap it up, wrap this topic up.